So this is the process flow diagram of obtaining sulfur from the iron pyrite. So what we are getting, so iron pyrite, so here we are using 200 mesh, so we are grinding in rotary kiln to get this get the iron pyrite, and we are passing through the 200 mesh. So here FeS2 we are feeding to the decomposition tower. So you can see fuel oil is passed over here, so that will be burned, creating the heat. So decomposition tower, it will decompose the FeS2. So what we get after decomposition? So decomposition we get the sulfur and the FeS. So here we can get FeS, and the other gases we are sending to the next stage. So here whatever the FeS we are getting, so here we are getting the limestone. So limestone we are using to remove the any particles over here. So collected over here, the FeS molten form, it will be collected over here. Water impurities over here, that we are collecting by the reaction with the limestone over here. Then molten FeS we are granulating in granulator, and then we are passing this to the sulfuric acid plant. Then what are the gases over here that we are passing over here? So whatever the heat the evolved over here, that we are sending, or here we are getting the water which is heated by the heat evolved over here, and we can get the 70 atmosphere steam, and that we can pass to the electricity generation. Then here it will decompose, then the gases which is coming over here, so that we are feeding to the hot reactor, and before that we are passing to the electrostatic precipitator. So whatever the waste gases over there, so that can be removed over here, and then the gases comes over here, and that will be reacted. So temperature will go up to 600 degrees Celsius, and then with the help of water as a coolant in a heat exchanger, we are making the temperature from 600 degrees Celsius to 150 degrees Celsius, and here also we can get the steam of 4.5 atmosphere that we can send to the turbo generator to form the electricity. So here is the hot reactor, because temperature is high over here. So from here we are getting the heat out, and then we are cooling it down. We are feeding it to the cold reactor, which works, and the temperature will go around 200 degrees Celsius, and then the converted one will go to the condenser to cool. Then here we get the steam of 0.7 atmosphere, that is low pressure steam we will get over here. And then the molten sulfur we are getting in this storage one. So what we are doing over here, so here molten sulfur will get, that we are washing with the calcium hydroxide to remove the arsenic and waste. So here it is necessary to remove the arsenic, because if arsenic over there, then that will affect the vanadium pentoxide, which is the major catalyst in sulfuric acid production. So the sulfur which we are recovering is generally to form the sulfur dioxide and sulfur trioxide, and then to the sulfuric acid. So here the arsenic become the ill element over here, and it will poison the vanadium pentoxide. So we are removing with the help of calcium hydroxide over here, and that sulfur, molten sulfur, we can ship over here. Here the stack gases we can wash into the wash tower, and the sulfur we are again feeding to here, and the waste we can remove over here. Then what happens over here, we are already removed the FeS, and we are shipped to the sulfuric acid plant. Then whatever the FeS and the SO2 we are getting over here, so that we are feeding to the fluidized roaster, and we are combusting with the help of air. Then water is to cool, and we get over here the 60 atmosphere steam because of the heat evolution. Then we are cleaning the gases in the cyclone separator and the electrostatic precipitator. So here whatever the Fe2O3 we are getting, which is formed in the fluidized roaster, so that we are sending to the iron ore, or that is used in steel plants. And the gases, that is SO2, which we are getting after the precipitator, that we are sending to the sulfuric acid plant. So here the iron pyrite in the we are meshing in 200 mesh. So FeS2 we are feeding to decomposition tower, the gases we are feeding over here, then we are purifying them with the help of electrolytic precipitator to clean the flue gases, and then we are feeding to hot reactor at around 600 degrees Celsius, which is cooled down to 150 degrees Celsius and fed to the cold reactor, and the sulfur which is formed is condensed over here. So the sulfur here we get, and we are washing with the calcium hydroxide to get rid of the arsenic and waste, and the sulfur we are feeding to the, or we are sending to ship. Then here, after limestone and the collecting the impurities, the molten FeS, we are sending to, after solidifying, to the sulfuric acid plant. And then remaining one in fluidized roaster, which will form Fe2O3 and which will form the sulfur dioxide, which is cleaned in cyclone separator and electrolytic precipitator. So that sulfur dioxide we are sending to H2SO4. And the Fe2O3 we are sending to the steam plants as an iron ore. So here, so whatever the heat evolved over here, so that is 70 atmosphere steam we are getting over here. Then the heat removal we get 4.5 atmosphere steam. Then the low heat removal we get 0.7 atmosphere pressure steam. And then the heat removed over here we get the 16 atmosphere steam. So this we are feeding to the turbo generator to form the electricity. So that's how we are getting the molten sulfur and the sulfur dioxide with the use of Fe2S2. So here what are the major engineering problems? So here the pyrite over beneficiation is the major engineering problem over here. Then grinding FeS2 to fine. So we have seen it has to be grind up to 200 mesh. So here grinding is necessary to get the more heat transfer and the more the reaction rate. So that also the major engineering problem. Then substitution of a coal for the fuel oil. So we can see the efficiency of the coal and fuel oil, they are different. So we have to decide whether we can use the coal or fuel gas to have the better heat recovery. Then the gaseous reaction in the smelting furnace, so the temperature will go very high, so that becomes a major problem. Then again, two-stage catalytic reactor design, the same as we have seen previous one. Then the heat recovery and the generation of the electric energy. So whatever the heat generated, that we are recovering to produce steam, and steam we are feeding to generate the process steam. So that also the design of this one becomes the one of the major engineering problem in the sulfur recovery. Then we have seen the sulfur recovery from the Frost process, then from H2S and from the iron pyrite. So there are other processes that were used to recover the elemental sulfur. So they are the Orkla process. So here the sulfur from cuprous pyrite. So we have seen CuFeS2 was used to recover the sulfur. So this was used in Norway. So it was in Norway based mining company, and 80% sulfur recovery by smelting pyritic copper ore with carbonaceous reducing agent. So here the sulfur which we are getting, so that was coming from the smelting pyritic copper ore. Then the next one was the Noranda process. So here the heating pyrite at around 540 degrees Celsius without oxygen to recover half sulfur in elemental form. And the last one was Outokumpu process. So this was Finland's largest company, and the elemental sulfur and iron cinder from the pyrite ore. So the Orkla, Noranda process and Outokumpu that were used before to recover the sulfur. And lastly, if we see the economics of these processes, then we can see the USA furnishes about 60% of world sulfur. So we can see the sulfur consumption is more in USA, whereas if you see the India picture, the sulfur consumption is very low in India. Then increasing quantities expected from Mexico via Frost process and from Canada and Europe via the natural gas process. So the major demand for the Frost process to recover sulfur in elemental form. Also Canada and Europe, they are dependent on the natural gas process for the sulfur recovery. So we have seen the sulfur production. So the main use of sulfur is to form the sulfuric acid. So you can see over here in laboratory also you have seen the sulfuric acid. which is hot and burning, we can see here the sulfuric acid and we can have the fumes over here. So just remember this fume because we'll deal why these fumes comes. So that will deal in the next part of this module. So if we see the history of sulfuric acid, then it was an important item of commerce in 1700. Then in 18th to 19th century, the production of sulfuric acid mainly by the chamber process. So we will not discuss about the chamber process, but we will discuss about the newer process of the sulfuric acid production. And the product containing 77 to 70% sulfuric acid, hence not much commercialized. So here nowadays we need more than 98% concentrated sulfuric acid. So there it was 77 to 78% of sulfuric acid. So it was not being commercialized at that time. Then earlier what they were using the platinum as a catalyst in the contact process. So the platinum used as a catalyst for contact process in early 20th century to get the high strength acid. You see over here, the platinum is very expensive. So whatever the acid, which high strength acid we are getting, that also becomes the expensive because of the platinum one. So that was in early 20th century. In 1875, Winkler stated process of conversion SO3 from SO2 effectively. So the yield of SO3 from SO2 conversion was increased, and that was developed by the Winkler in 1875. Then 1915, the Bradish used vanadium as a catalyst for the above process. So here it was the platinum and it was replaced by the vanadium pentoxide. So the platinum, which is far expensive than vanadium, so the cost of the sulfuric acid came down tremendously, and this process became the more useful nowadays. So nowadays the sulfuric acid manufacturing takes place with the use of vanadium pentoxide as a catalyst. So if we see the 100% sulfuric acid properties, so it has a molecular weight around 98.08. It melts around 10.5 degrees Celsius and the boils with decomposition around 340 degrees Celsius. If you see the solubility, so it is completely miscible with water with large heat of solution. So if we dissolve sulfuric acid in water, we can see the fumes are coming and also the temperature of water increased tremendously. So why? Because with the hydration, it's an exothermic reaction for the sulfuric acid. Then the sulfur trioxide soluble in H2SO4 to give varying percentage of oleum. So oleum, we'll see what is meant by the oleum in the next part. If we see the grades of acid, so generally the concentration of sulfuric acid earlier it was giving in the Baume. So if we see 50 degree Baume, so it contains 62.2% of sulfuric acid, and the specific gravity if we say at 18 degrees Celsius it was 1.525. If we see the 60% Baume, the percentage sulfuric acid we can find 93.5. In 95% and 98% grades of sulfuric acid, so they will have percent of sulfuric acid of 95 and 98. And specific gravity 1.84 and 1.843 respectively. Then the monohydrate acid we say for the 100% sulfuric acid. So it is having the gravity 1.834. Then if we say the 20% oleum, that is fuming one. So in oleum we can say it's a mixture of the sulfur trioxide and the sulfuric acid. So in this one 1.45% sulfuric acid and the 20% free SO3. Means how we get this one? So whatever the SO3 that can be converted in H2SO4, so that will lead to the total percentage of sulfuric acid. Similarly, if we said 40% oleum, that means 109% of sulfuric acid and 40% free SO3. And for 65% of the oleum, it's 114.6% of sulfuric acid and having 65% of free SO3. The gravity for the oleum, specific gravity, it will increase. So if we can say sulfuric acid, so very less concentration is 1.5, then moderate concentration 1.8, and for the oleum it has increased to 1.9. So the for 20% is 1.924, for 40 it is 1.963, and for 65% it is 1.987. So you can see over here, as the concentration of oleum increases, the specific gravity also increases. So in other words, we can say, if you know the specific gravity, we can find out the percentage oleum present in the sulfuric acid. So we can see this historically, concentration of sulfuric acid is reported as degrees Baumé, and that is denoted by the degree and capital B and E. And if you know the specific gravity, we can state as degree Baumé as 145 minus 145 divided by specific gravity at that temperature. And it is valid up to 93% because above density is not a function of concentration. So this formula is valid up to 93%. Above which you can see, so above which it's not a linear function. So above which density is not a function of concentration. So if we see the graph, it is a sulfuric acid in water, that is waste percentage, and that we are getting at 15 degrees Celsius oblique 4 degrees Celsius. So here if we see the sulfuric acid in water, so specific gravity and the sulfuric acid in water weight percentage, it's a linear up to 93%, and above which it's non-linear. So at this percentage we can find out what is the specific gravity from this graph. So when this graph is given, we can find out the specific gravity and the corresponding degree Baumé, how to represent it. Then sulfuric acid in water versus critical temperature. So you know the sulfuric acid, when dissolved in water, it will evolve the heat. So that heat is heat of hydration. So we know the sulfuric acid is a strong dehydrating agent. So when this spills on your skin, it will dehydrate your skin and you get the burning sensation. So and heat also evolved. So here sulfuric acid in water, if a weight percentage, and we plot versus the critical temperature in degrees Celsius, then we can see as the sulfuric acid in water increases, the temperature also increases. So up to this point, it's a linear function, and above which it becomes a non-linear function. So we can see at 0% also, it is showing this critical temperature. So if you add the water, it will be evolved, and it will show the higher temperatures up as the water in sulfuric acid increases. Now we will see what is meant by the oleum. So oleum strain is usually reported as weight percent free SO3 or percentage equivalent of sulfuric acid. And we can calculate percent sulfuric acid as 100 plus percentage oleum by 4.444. So if we use this formula, then 20% equivalent to 104.5% of sulfuric acid. So 20% oleum, so 100 plus 20 by 4.444, so that will lead to 104.5% of sulfuric acid. Then oleum is generally considered as a mixture of sulfuric acid and the free SO3. So whenever oleum word, if you find, it is nothing but the sulfuric acid, and SO3 is dissolved in the sulfuric acid. Then what are the methods of manufacture of sulfuric acid? So there were chamber process earlier, and nowadays we use the contact process, which we can again subdivide as single contact process and the double contact process. Both are based on the sulfur dioxide. Chamber process is less concentrated acid, hence it's virtually obsolete. So here the chamber process is yielding the less concentrated acid. So nowadays we don't use chamber process, but we go for the contact process to have the high strength acid. The contact process is more than 98% of acid, and which can be diluted if necessary. So we can have the 98% acid, and if we want the less diluted acid, then we can make it less diluted after obtaining the concentrated one. So that is the advantage of contact process over the chamber process. Then if you see the contact process, so if you see chemical reaction, so first what, the sulfur reacting with the oxygen, giving the sulfur dioxide. So this is the exothermic reaction, and heat is evolved over here. then that sulfur dioxide is converted to sulfur dioxide with the reaction of the oxygen. And here we are using the vanadium pentoxide as a catalyst. So here it's again a exothermic reaction, and it was hit around minus 23 kilocalorie per mole of the reactant. Then the sulfur dioxide with water, we get the sulfuric acid in liquid form. Again it's an exothermic reaction. So here we can see at each stage heat is evolved. So if we see the process flow diagram, we can see heat is evolved tremendously, and that to be recovered. So this first thing is sulfur dioxide from sulfur and oxygen, then sulfur trioxide from sulfur dioxide and oxygen, and then lastly that sulfur dioxide with the reaction with water, we can get the sulfuric acid in the concentrated form. Here main thing is catalytic conversion of SO2 to SO3. So we'll see what is meant by that. So according to the Le-Chatelier's principle, a lower temperature should be used to shift the chemical equilibrium towards the right, hence increasing the percentage yield. So here, if a reaction is exothermic, then what happens? The reaction is exothermic, so if you want to have the forward rate of reaction, the product should be high. So what we have, we should lower down temperature, or to shift equilibrium from to the forward side, we have to take care of the heat, and we have to remove the heat simultaneously. So can the equilibrium can shift from the left hand side to the right hand side. So this is given by the Le-Chatelier's principle. Next one, too low of a temperature will lower the formation rate to an uneconomical level. But while doing that one, we should take care that temperature is not too low. If the temperature is too low, then what happens? The conversion will not be much. So what things? We want the low temperature also, and we want not a low temperature to have the unreacted the sulfur dioxide. So what we have to maintain the balance of temperature in this reactor. Then hence to increase the rate of reaction, what we can do, we have to combine both the things. So high temperature, that is 450 degrees Celsius, medium pressure 1 or 2 atmosphere, and the vanadium oxide are used to ensure 96% conversion. So here, so what happened? Heat is evolving, so we are removing the heat, but not much to carry out this. So the equilibrium will shift to this side, and we get the sulfur trioxide. So for this reaction mainly, if you want more SO3, we have to remove the heat. So SO3 formation will be high. So here we are using the vanadium pentoxide. Also, the pressure over here is high, means the concentration of O2 and SO2, if they are very high, the reactant, one is in very excess, then it will lead to SO3 concentration. So O2 we can have the higher quantity, because O2 available from here is very cheap. So we can have the excess of O2. But the problem with this one, if we have the high O2, SO3 will be very high. But increasing O2 concentration, the SO3 concentration will decrease in the air. So for this one, we have to maintain the equilibrium concentration of the air and the O2. So here we are using the catalytic converter. So the catalyst only serves to increase the rate of reaction and does not change the composition of the thermodynamic equilibrium. So catalyst is used to only to increase the rate of reaction. It will not take part in the reaction, and it will not disturb the thermodynamic equilibrium. Here we are using the vanadium pentoxide. So we will see roughly what is the mechanism for the action of catalyst. Comprises 2 steps. So if you see the catalyst activity, then the oxidation of SO2 into SO3 by V5+. So here vanadium 5+. So what happens? The sulfur dioxide comes as a reactant, then it will react with the V, which is 5+ valence, and the oxygen, and it will reduce from 5+ to 4+. So in first stage, vanadium will reduce from 5+ to 4+. In the next stage, oxidation of V4+ back into V5 plus by oxygen. So earlier stage what happened? SO2 into SO3, oxidation of SO2, and V5 is reduced over here. Next stage V4 will go to V5. So here the V4 plus stage is oxidized to V5, and then we can have here. So here the catalyst is regenerated. So we can see the catalyst reduced and catalyst again regenerated. So this is the effective catalyst we are using over here. Then hot sulfur trioxide passes through the heat exchanger and it dissolves in concentrated H2SO4 in the absorption tower to form the oleum. So whatever sulfur trioxide is formed, that we can dissolve in sulfuric acid to form the oleum, that is H2SO7 in the liquid form. So here the sulfur trioxide we can make more concentrated sulfuric acid, or we can use to form the oleum over here. So here the catalyst vanadium pentoxide, so oxidize and reduce and oxidize, and the sulfur dioxide which may go for the sulfuric acid production or maybe the oleum tower to oleum formation. So here what is the problem? Directly dissolving SO3 in water is impractical due to the highly exothermic nature of the reaction. So we have seen the SO3 when directly reacted with water, being an exothermic reaction, it will allow tremendous amount of heat, and that heat will lead to the vapor formation of water, and that will become the fumigant. So earlier picture of sulfuric acid, we have seen the fumes were coming. So that will happen if we react water directly with SO3. So SO3 in a plant, we can spray the water over it because of the fume formation. So acidic vapor or mist are formed instead of a liquid if this thing is done. So what happens? Oleum is reacted with the water to form the concentrated H2SO4. So rather than having the water reacted with SO3, we will first have the oleum and then we will add water slowly to form the concentrated H2SO4. The average percentage yield of this reaction is around 30%. So here oleum and the water, we can get the sulfuric acid of our desired grade.